We're supposed to determine whether this series converges absolutely, conditionally, or diverges. So the first thing you want to check is to see if we were to get rid of the alternating part of the sequence. If you take the absolute value, does this converge? Because if it does, if you make this positive, if this converges, then it converges absolutely. And if it doesn't, then we can check to see with the alternating series test to see if whether it converges conditionally. Otherwise, we're going to have to go with divergent. So we could use the comparison test or the limit comparison test, whichever one you think is going to be easiest. I'm going to compare it to the harmonic P series. And it's hard to directly compare these two, but if you rewrote this one as k squared over 6k plus 1 times k. I multiplied the top and the bottom by the opposite denominator just to get common denominators. And I'm going to multiply the top and the bottom of this fraction by 6k plus 1 over 6k plus 1k. This is still the harmonic series, right? It's still 1 over k when you simplify it. And what I did was I just got them to have common denominators. That way we could focus on the numerators. It's clear to see that the numerator is going to be bigger than the numerator in this fraction because it's k squared, and we're summing k equals 1 to infinity. Okay, we studied that with like horizontal asymptotes. The square power is always going to outpace the first power. So we can say that this is going to be greater than this fraction. So the series we have here is greater than the harmonic series. And from our work in the textbook, this diverges. And from the limit test, we know that if you have a fraction that's greater than a divergent series, then that fraction must also diverge. So we just found out that this diverges because it's greater than something we already know to be a divergent series. So it doesn't converge absolutely. To determine whether it converges conditionally, now we want to apply the alternating series test. We want to see if the next term, is smaller than the current term, but we also need another condition to hold. We need the limit as n goes to infinity, or in this case as k goes to infinity, of k over 6k plus 1. This has to equal 0, but it doesn't, right? There's a 1 in the numerator, there's a 1 in the denominator. So it's a ratio of the leading coefficients. This doesn't equal 0. The limit as k goes to infinity approaches 1/6. So what eventually you're going to see as k goes to infinity is that you're going to be adding 1/6 to the sum of your series, and then adding a negative 1/6 or something infinitely close to these. And it's just going to keep alternating back and forth by adding non-zero values. Okay, so the alternating series test says that this needs to hold true, and it actually does. This fraction is less than this fraction. You could prove it. But as k goes to infinity, I forgot what I was saying. Yeah, the limit as k goes to infinity for this fraction, it does not equal 0. So they're just going to keep the series is just going to keep alternating, adding and subtracting values of 1/6.